Section 1 Introduction. We'll be discussing an interesting shift in the interaction between humans and computers. Traditionally, a human would give a command to a computer, which would then execute the task. However, tools such as Amazon's Mechanical Turk have reversed this paradigm, allowing artificial intelligence to guide the human element. A common link between vast computer vision datasets and large-scale psychological studies is the reliance on crowd work performed on platforms like Amazon Mechanical Turk, Prolific, and Upwork. These crowdsourcing platforms are invaluable to researchers and industry professionals, enabling them to generate, categorize, and summarize various types of data, as well as conduct surveys and experiments. Simultaneously, large language models, LLMs, such as ChatGPT, GPT-4, Palm, and Claude, have emerged as a force in the digital realm. Initial research indicates that LLMs are fantastic at annotating data, surpassing both crowd workers and subject matter experts. They also seem to be capable of mimicking human behavior, which allows social scientists to carry out virtual experiments and surveys, yielding results similar to those obtained from actual humans. However, human participants in these experiments, as well as those who annotate and take part in surveys, remain skeptical about the validity of results from LLMs, as these models still underperform in some tasks and the synthetic data they generate can differ significantly from real, desired data. Given this, one might be tempted to use crowdsourcing to verify LLM outputs or to create a benchmark set of human data for comparison. But what if the crowd workers themselves are leveraging LLMs to boost their productivity, and consequently their earnings, on crowdsourcing platforms? We argue that if this were the case, it could significantly reduce the usefulness of crowdsourced data, as it would no longer represent the intended human benchmark. Additionally, it would be more cost-effective to directly prompt the LLMs instead of paying crowd workers who may be using these models without disclosing it. For these reasons, we're interested in determining the extent to which crowd workers are already incorporating LLMs into their tasks. This is critical for anyone depending on crowdsourcing because without knowing the true source of the data, humans or machines, it's challenging to understand how much trust to place in it. Our initial step towards answering this question involves a case study on Mechanical Turk, where we've developed a new approach to detect synthetic text. We focused on a text summarization task involving medical research paper abstracts. Our method, which combines keystroke detection and synthetic text classification, estimates that between 33% to 46% of summaries submitted by crowd workers were produced with the help of LLMs. Our findings suggest that despite their relatively early stage of development, LLMs are already contributing significantly to the textual data collected via crowdsourcing platforms, overshadowing the human crowd workers they're supposed to be assisting. Although our study is specifically about text summarization, we believe other text production tasks that can be easily prompted to an LLM may also be similarly affected. Furthermore, as LLMs continue to grow in popularity and as models capable of dealing with not just text, but also image and video inputs and outputs evolve, the implications are profound. Our findings should serve as a wake-up call to platforms, researchers, and crowd workers alike, highlighting the urgent need for innovative approaches to ensure the authenticity of human data in a world increasingly dominated by artificial intelligence. Section Summary. Crowd work done on platforms like Amazon Mechanical Turk, MTurk, and large language models, LLMs, have become central to researchers and industry practitioners for creating, annotating, and summarizing data, as well as running surveys and experiments. However, a case study on MTurk found that 33 to 46% of the text summaries produced by crowd workers were actually produced with the help of LLMs, which could severely diminish the utility of crowdsourced data. This study serves as a reminder to find new ways to ensure that human data remain human. Section 2 Related Work. In this section, we'll discuss related work, which is divided into several subsections. Research involving crowdsourcing, studies about crowdsourcing itself, data generated by large language models, LLMs, and efforts to distinguish between LLM-generated and human-created content. When Amazon Mechanical Turk, also humorously referred to as artificial intelligence, was first introduced, it revolutionized task outsourcing. Users could upload tasks to the platform, and while it might have seemed like an AI was doing the work, it was actually accomplished by people. This platform opened up new avenues for creating machine learning datasets, conducting user studies, and carrying out social science experiments by enabling tasks like transcription and image annotation to be crowdsourced. This surge in crowdsourcing, fueled by the advent of Amazon Mechanical Turk and subsequent platforms, resulted in a plethora of studies dedicated to understanding it. This research aimed to find efficient ways to leverage the power of crowdsourcing despite its limitations. Investigations were made into the quality of work produced, as well as the demographic and socioeconomic status of the workers who use these platforms. Large language models, or LLMs, have also attracted attention due to their ability to mimic certain human subgroups effectively, a phenomenon we'll refer to as silicon samples. Most research in this area involves a specialized form of controlled text generation. As we've seen, LLMs are not only useful for impersonating humans in experiments but also for generating high-quality, albeit often factually incorrect, text that has caught the attention of both the public and the media. However, a major concern that arises is the difficulty in distinguishing text generated by LLMs from that created by humans, a task which is challenging for both AI models and humans themselves. As an illustration, even OpenAI's own model for identifying LLM-written text can correctly identify it only 26% of the time. This has sparked worries about the use of LLMs like ChatGPT in areas like social media and higher education, where they could be used for generating spam, misinformation, or even to cheat on assignments and exams. This has, in turn, led to further studies on methods of watermarking, or subtly altering LLM outputs, and enhancing the detection of synthetically generated text. Section Summary. The section discusses the impact of crowdsourcing on machine learning datasets and user studies, as well as the use of language models, LLMs, as proxies for human subpopulations. However, distinguishing LLM-generated text from human-generated text is difficult, leading to concerns about their usage in areas such as social media and higher education. Work has been done on watermarking LLM output and improving the detection of synthetically generated text. Section 3 Methods. The diagram and figure showcases our approach, which we will elaborate below. Our chosen task is abstract summarization. This task, initially designed for an M-Turk experiment, was intended to investigate the telephone effect, the phenomenon where information gradually becomes lost or altered as it passes from one person to another in an information cascade. In the original experiment, participants were given medical research paper abstracts from the New England Journal of Medicine, NEJM, on topics like vaccination, breast cancer, cardiovascular disease, and nutrition. Their task was to condense these long abstracts, approximately 2,000 characters long, into shorter paragraphs of around 1,000 characters. The task continued in iterations where the summarized texts were summarized further in multiple rounds. We selected this task for our study because, first, it is a task that can be quite tedious for humans but can be easily accomplished with the help of commercially available language models. Second, the task demands genuinely human-generated text as it explores the information loss when humans summarize texts, an exploration that can't be done with synthetically generated data. In the original experiment, the workers provided 8 progressively shorter summaries of each abstract. For our purposes, we simplified the task to a single summarization step, where each abstract was condensed into a summary ideally of about 100 words. The workers were paid 1 for each summary they created, a task that we roughly estimate to take about 4 minutes, leading to an hourly wage of 15. From this process, we collected 48 summaries from 44 distinct workers. However, 2 of the summaries were duplicates, so after removing these, we were left with 46 unique summaries, all written around June 1, 2023. Additionally, we captured all the keystrokes made by the workers during the task, including copy and paste actions. These actions were tracked either with keyboard shortcuts, Ctrl+C and Ctrl+V, or mouse operations, like using the right-click menu. Please note that our work is ongoing. We will continue with the task and update this preprint as necessary. Section Summary. The authors modified a prior M-Turk task to study the telephone effect in abstract summarization, where information is gradually lost or distorted as a message is passed from human to human. Crowd workers were given medical research paper abstracts and asked to summarize them into a much shorter paragraph, which was then iterated for multiple rounds. The authors obtained 46 summaries written by 44 distinct workers and also extracted all keystrokes made by workers while performing the task. Section 3.2 Detecting Synthetic Text. In this section, we're going to talk about how we detected synthetic text, particularly in the context of our task, which was to summarize text. The challenge was to find out whether the summaries provided by crowd workers were created by humans or artificially generated. While there are a number of tools available for detecting synthetic text such as GPT-0, OpenAI's AI detector, or Writer, these solutions didn't perform well for us. For instance, of 10 summaries that we created using ChatGPT, GPT-0 could only correctly identify 6 as synthetic. Given this, we opted to create a tailored solution for identifying summaries generated by large language models, LLMs, specifically ChatGPT, which, at the time of writing, is the most commonly used LLM. Our approach, although applied to only a few summaries in this study, is more efficient for larger future datasets where using API calls could be costly and slow. Now, Let's talk about the architecture of our model. We used an E5-based pre-trained model as our main framework. This model, pre-trained with a contrastive loss, demonstrated strong performance in a classification setting when fine-tuned. During this fine-tuning process, we used a learning rate of 2 multiplied by 10 to the power of -5, a batch size of 32, a maximum token length of 256, and trained for 5 epochs, while saving the best performing model on the validation set for later use. As for the data used to train our classifier, we utilized 3 datasets, all originating from or inspired by the Mechanical Turk, MTurk, task under investigation. The real instances of human text included 16 original abstracts and the actual human responses, 128 high-quality summaries. We generated the synthetic instances by prompting ChatGPT with the MTurk task instructions, a tactic we believe many crowd workers also employed since they often copied these instructions, which we noted through keystroke logging. For each abstract, we produced 10 different summaries for each of 2 temperature values, 0.7 and 1, resulting in 320 synthetic samples. We trained the model in 2 setups, one with an abstract level split and one with a summary level split. In the abstract level setup, we divided the abstracts into 2 distinct sets, 12 abstracts for training and validation, and 4 for testing, totaling 370 training points. The purpose of this setup was to see how well our model could identify synthetic summaries of abstracts it hadn't seen during training. For the summary level split, we randomly divided both the real and synthetic summary datasets, using 75% of the summaries for training, 10% for validation, and 15% for testing. Finally, to verify the accuracy of our results, we used a set of heuristics to judge whether specific subsets of our data were generated by humans or synthetically, based on logged keystrokes. First, we assumed that summaries written entirely in the text box provided on MTurk, without any text being pasted in, were human-made. This helped us evaluate the false positive rate of our classification model. Secondly, for summaries where pasting was used, we examined the portion of pasted text that originated from the abstract and the portion that was new text. If pasted summaries didn't correlate much with the original abstract, we assumed they were synthetically generated, which helped us gauge the false negative rate of our model. Section Summary. The paper discusses the need to detect whether crowd workers' answers were synthetically generated to estimate the prevalence of LLM usage in summarization tasks. Out-of-the-box solutions such as GPT-0 fail to perform effectively, so the authors rely on a bespoke solution by fine-tuning their own model to detect the usage of ChatGPT, the most commonly used LLM. The model was trained on 3 datasets and validated using heuristics to assess whether specific subsets of the data were synthetically generated or human-generated. Section 4 Results. We're discussing the outcomes of our study about the performance of a synthetic text detector in this section. The detector was used to distinguish between genuine and synthetically created summaries and abstracts. Let's first talk about the summary level evaluation. In this setting, we combined summaries from all abstracts before diving into the data. Our refined model proved to be highly efficient, with an accuracy of 99% and a macro F1 score, which is a measure of model performance, also at 99%. This remarkable outcome suggests that there is a lack of diversity in the summarizations by ChatGPT, a language model that we trained using RLHF methods. Interestingly, our less complex detection model was able to identify unique patterns, or fingerprints, that ChatGPT had created. These fingerprints were present across all abstracts, which suggests they are a common feature. Even when our model hadn't seen a certain set of abstracts during the training phase, it still managed to correctly spot synthetic summaries 97% of the time, maintaining a macro F1 score of 97%. This indicates that a ChatGPT detection model trained solely on our abstract summarization task can identify newly synthesized abstracts almost all the time. The high-performance scores are evidence that there's an identifiable ChatGPT fingerprint in abstract summarization tasks that helps it learn how to differentiate between genuine and synthetic texts. Moving on, we utilize the summary level model to detect instances of language model usage among crowd workers. In this case, we had to establish a decision threshold. If a text was classified above this threshold, it was identified as synthetic, and if it was below, it was marked as human-generated. To ensure our method was reliable, we used a variety of threshold levels and showed how the percentage of summaries classified as synthetic changed with the threshold level in a graph. With a logit threshold set at 0, which corresponds to a 50% predicted probability, we estimated that 21 out of the 46 crowdsourced summaries, or 46%, were synthetically generated. However, to minimize misclassification of ambiguous examples as synthetic, we might want to choose a more stringent threshold. If we increase the threshold to 4, 98% predicted probability, we estimate that 33% of the summaries were generated by language models. Despite the wide range of threshold levels, our estimate stays consistent, suggesting that 33 to 46% of the summaries provided by the crowd workers were created with the help of language models. It's worth noting that almost all users contributed just one summary. Therefore, the estimated percentage of language model-generated summaries can also be seen as the fraction of crowd workers who used language models. Next, we validated our approach after estimating the prevalence of language model usage. The majority of users seem to have copied and pasted some text while creating their summaries. Indeed, only 5 summaries were written entirely in the text box without any pasting, all of which our classifier labeled as human-written, implying a low false positive rate. However, the mere act of pasting doesn't necessarily imply the usage of ChatGPT. Our observation suggested that workers often borrowed complex phrases, or even entire abstracts, from the original text, thereby reusing content. To explore how copying and pasting was used in the summaries that were classified as synthetic or human, we calculated the longest matching sequence between each summary and the original abstract. Our analysis revealed that workers often used large sections from the original abstracts, but, notably, summaries that were classified as synthetic generally had little overlap with the original abstracts. For example, out of 13 summaries with less than 10% overlap with the original abstract, 10 were identified as synthetically generated. Also, most of the synthetic summaries had a small overlap with the original abstract, suggesting that what was being copied and pasted were not parts from the original abstract, but outputs from a language model. Section summary. The synthetic text detector achieved high accuracy and macro F1 scores in identifying synthetic summaries, indicating a lack of diversity in ChatGPT summarizations. The model was able to successfully identify new synthetic abstracts almost all of the time, suggesting the existence of an identifiable ChatGPT fingerprint in abstract summarization tasks. The prevalence of LLM usage among crowd workers was estimated to be between 33 to 46%, with a low false positive rate and evidence that workers often copy-paste outputs from an LLM rather than parts from the original abstract. Section 5 Discussion. In our discussion, we underscore the importance of human-generated data for a variety of applications, because of its unique and diverse characteristics, which make it distinct from synthetic data. Our findings revealed that individuals working on the mTurk crowdsourcing platform often utilize large language models, LLMs, for summarizing tasks. This brings up important questions about the decreasing influence of human input in crowdsourced textual data. We also devised an effective and computation-friendly method to identify synthetic data, suggesting that custom-made detection models might be more beneficial than generic solutions. This method can be applied in other areas where synthetically generated content may cause issues. For example, in education, where tests, essays, and assignments could be easily completed by LLMs. There's a growing fear that LLMs might drastically change our information landscape by generating a large portion of the information available online. This could potentially harm the performance of recursive LLMs, those trained on synthetic data, and magnify the influence of the inherent values and ideologies encoded in these models. Our study also raises the issue that obtaining genuine human data could become more difficult due to the widespread use of LLMs by crowd workers. This problem could escalate with the increase in popularity and capabilities of LLMs. However, we don't think this will mean the end of crowd work. It might just bring about a fundamental change in the value offered by crowd workers, who might serve more as a human filter for identifying when LLMs perform well or poorly. Pioneering research has shown promise in coupling human skills with language models to produce high-quality and diverse data. We should note, though, our study has a specific focus on one type of crowdsourcing task, text summarization, which does encapsulate many aspects of general text production tasks. But we're aware that the applicability of our findings to other tasks, particularly those posing significant challenges to LLMs, is uncertain. This uncovers an important future research avenue to investigate how results may differ across various tasks and how they change over time with the increasing use of LLMs. We theorize that any text production task that can be guided by a textual instruction easily interpreted by an LLM might be impacted by the trends we've identified. Thus, our findings should serve as a caution for those working with different data types and tasks. Section summary. The use of language models, LLMs, by crowd workers in text summarization tasks raises concerns about the dilution of the human factor in crowdsourced data. The study also developed a low-cost method for detecting synthetic data, indicating that bespoke detection models may be more useful than out-of-the-box solutions. The popularization of LLMs may make acquiring human data even harder, But crowd workers may still serve as an important human filter for detecting when these models succeed and when they fail.